Section 9.1, Inferences for Regression, video number 5. The last skill we're going to learn in section 9.1 is testing correlation. Recall that correlation for a sample was the variable R, and it's a measure of the linear association, emphasis on the word linear, between two quantitative variables. The variable for population correlation is the Greek letter rho, which kind of looks like a lowercase p, little curvy, little tilted. Why are we testing correlation, specifically correlation equal to 0? Because if correlation tests to be 0, that means that there is no linear association. So we'll be doing a hypothesis test to see whether or not we can conclude that the population correlation is equal to 0. More specifically, if there's not enough evidence to conclude that it's not equal to 0. For example, no surprise, we're going back to the same context. We're going to test if there's a linear association between the printing speed and the price of the printer. Now, we still have the critical value approach and we still have the p-value approach. In this case, we're going to use only the critical value approach. The main reason is we're not going to be given the p-value, and unless we have the correct technology, we're not going to get the p-value. I stand corrected. We could actually extract a range of p-values from the t-chart, so maybe we'll take a look at the p-value approach as well. But let's take a look at the critical value approach. As with all hypothesis tests, step number 1 is to state the hypotheses. We already know that we're testing whether or not rho is equal to 0. That would be the null, since it allows equality. In fact, it demands it. And the alternative would be that the population regression is not equal to 0. If you wanted to write these hypotheses in words, saying that the population regression is equal to 0 is saying that there is no linear association. And of course, saying that the population regression is not equal to 0, the population correlation is not equal to 0 is saying that there is a linear association. It might be a weak linear association, but it's better than having none. If we were to take the critical value approach, the first thing we'd have to do is calculate the critical values. Again, we're using a 5% significance level since we weren't told otherwise. Two-tailed test because the alternative is not equal. So same picture as before, 2.5% in each tail. Non-rejection region in the middle, 2 rejection regions since it's a two-tailed test. Degrees of freedom is still 18. The formula was n minus 2. And we're still going to get t equals plus or minus 2.101 for our critical values. So what's our test statistic? Well, it's a formula. The formula for the test statistic is what we get from our sample, which is R, minus what we're hypothesizing, which is 0, divided by a standard error. Now, this standard error is not given to us. Sorry, something made a noise. I was just seeing what it was. This standard error is not given to us in our computer output, but there is a formula for it. The formula for the standard error when testing correlation is a tall square root. On the top of the square root is 1 minus r squared. And on the bottom of the square root is n minus 2. So we actually have to calculate the standard error. But there's one thing that we're missing. What is r equal to? Well, we weren't given r, were we? Don't believe we were. Now, I know where to get it from, I just haven't told you yet. Just seeing if there's somewhere here that they gave it to you. This is where I would pause the video, but if I pause it, then I have to start over, and I don't really want to do that. In the example on page 581, they do give you the value of R. But there's something about it that bothers me. Oh, because that's a different type of problem, my mistake. Okay, so we don't have the R. So where does the R come from? Well, I guess now's the time to tell you. The R is hidden in the computer output. And you may have noticed there was something on the bottom of the computer output that I didn't allude to, but we're going to capitalize on. So go back and look at the computer output that was originally on page 577. It's also on page 579. And by the way, this is not the example on page 581 because they're comparing two different variables. One of them is not price. So we can't use example 9.2 on page 579. But nonetheless, I know what's going on here. So how do we get the R where we don't have the R? The answer is the value of R squared back in the computer output. So just a little side note here. I'm going to move this up here. And we're talking about how to get R. To get R, you have to do two things. Number one, from the computer output, you'll notice that there was a value for R squared. That is the same R, it's just squared. There's a reason it's squared, you'll see why soon. The value of R squared was 54.7%. R squared was 54.7%, which is a decimal, is 0.547. So that is the same R, it just got squared. So guess how we're going to get R? We're going to square root that. But here's where you have to be careful. Square rooting the R squared is not an issue. Just get out the technology of your choice and ask it to square root 0.547. Here's the problem with just square rooting it though. Algebraically speaking, when you square root a number, it always comes out positive. However, correlation can be positive or negative. So when we square root the R squared value, how do we know if it's supposed to come out positive or negative? And the answer is, look at the slope. The slope of this line was 90.88. That means it's a positive slope, which means the line goes up. Well, if the line goes up, it's a positive association, and therefore the correlation should also be positive. So here, use a calculator to square root the value of R squared to 4 decimal places. I get 0.7396. But this could be positive or negative. Positive if the slope is greater than 0. Negative if the slope is less than 0. Because the sign of the correlation and the sign of the slope have to be the same. Positive slope, positive correlation. Negative slope, negative correlation. Since the slope on this line was positive, so must the R. So to get R from the computer output, square root the R squared value. If the slope is positive, your R is positive. If the slope is negative, the R is negative. So not too tricky to do, but it's not just out there saying, do this. Let's get back to the test statistic. Our standard error is going to be the square root of 1 minus R squared. Wait a minute, R squared. Wasn't R squared 0.547? You could square the value of R and you'll get something close to this, but they gave you R squared, so I would just use it. And the value of N was 20, because there were 20 ordered pairs. And so if we put all that in the calculator carefully, 1 minus 0.547 equals, we're going to divide that by 18, and then we'll take the square root of that. Don't forget to take the square root. 0.1586. And so our test statistic is going to be the value of R, which was 0.7396, divided by the standard error, 0.1586. And let's see what that is. If I can type, 7396, 1586. 4.663. Well, that looks awfully familiar. Wasn't that the same test statistic that we had? Or it was. But that was a totally different setup. My mind's a little bit perplexed that this test statistic, when testing correlation, came out to be the same as the test statistic when testing whether or not the slope was 0. I'm not saying that they're always equal, but that's going to bug me for a little bit. I digress. Here's our test statistic. Lands in a rejection region, and so we're going to reject the null hypothesis. Therefore, we conclude that the correlation is not equal to 0. Therefore, we conclude that there is a linear association. So it's just a hypothesis test with critical values and test statistics and all that jazz. By the way, the formulas for the test statistic is on page 581. They don't explicitly say, here's the formula for the standard error. They embed it inside of the formula for the test statistic. In other words, they take this square root and cram it under this fraction. I don't want to do that. Could we use a critical value approach? Well, sort of. Excuse me, we just did the critical value approach. Could we use the p-value approach? Sort of. This is our test statistic. The p-value is the area of the tail cut off by the test statistic. So if we wanted to find that area of this t, excuse me, we would have to go to the correct row for degrees of freedom, and I know you can't see this, but if I go to the 18th row for the degrees of freedom and look for our test statistic, it won't be in there. So we look for two values that it's between. But the t-values going across on the 18th row are 1.330, 1.734, 2.101, 2.552, still not here, 2.878, and then the last one is 3.610. This t-value is bigger than the largest t-value in the 18th row in the table. What does that mean? Well, the last t-value is associated with the tail area of 0.001. So if the t-value goes further out to the right, it creates a smaller tail. So what we know about the p-value is that it's less than 0.001. Well, if the p-value is less than 0.001, then it's definitely less than 5%. We would reject the null hypothesis and draw the same conclusion. But I don't like saying that the p-value is between these or is less than this. I like to know what it actually equals. So without technology, we couldn't grab the value of the p-value easily, so we'll just stick with the critical value approach.